So let's do a couple examples of variance here. It says find the variance of a given sample of data in the previous example, 2, 4, 7, 12, 15. So the first thing I want you to do is go back and look. We have already found the standard deviation of this problem. When we found it was a sample, the sample standard deviation was 5.43. So to find that variance, all we're going to do is take that sample standard deviation and square it. So take 5.43 and square it. I'm getting approximately 29.5. That would be my variance for this data. Same thing with number 10, find the variance. Again, we're looking at variance. All variance is the standard deviation squared of the given sample space 5, 8, 16, 17, 18, 20. Well, this is one of the first data sets we did in this packet. We already found the standard deviation for this. This was a sample, so it's the sample standard deviation that we're using. We had a sample standard deviation of 6.03. So to find that variance, all we're going to do is take that sample standard deviation, square it, so that's the 6.03, square it, and I'm getting 36.36. Or 36.4 if we rounded it to one decimal place. It doesn't really matter. Okay, so all variance is the square of a standard deviation. It says, although the variance of a set of data is an important measure of dispersion, it has a disadvantage that it is not shared by the standard deviation. The variance does not have the same unit of measurement as the original data. So if the original data was in terms of dollars, the standard deviation would be in terms of dollars. But the variance is messed up because it's that unit squared, so it's dollars squared. So what's that? It says, for instance, if a set of data consists of times measured in hours, then the variance of the data will be measured in square hours. The standard deviation of this data set is the square root of the variance, and as such measured in hours, which is more intuitive unit for the measure. So it's just saying, yeah, there is variance, and they do talk about variance, but you got to realize that the variance doesn't have the same units as the original thing, so we can't just take that mean that we were taking before and add and subtract the standard deviation. We can't do that same thing with the variance. The variance doesn't give us that nice comparison there. So we can't just take the mean and add and subtract the variance. We can only do that with standard deviation. Okay? So there's one last thing that's not on this that I wanted to talk to you guys about real quick. So what is this about? This is about, the reason I'm making these videos is I'm at home right now because of the COVID-19 outbreak, okay? We'd normally be in class, but what were we talking about? Well, this is a perfect example of when you want a large dispersion instead of a small dispersion. So let me give you a couple graphs right here. If you have something like this, where all the data values, this is your mean right here in the middle, okay? This one right here has a small deviation. Most of the data points are really close to the mean, whereas if we have something like this one right here, if this is your x-bar, this one has a large deviation. And that's because most of our stuff is away from the mean. Okay, so small deviation means it's accurate, everything's really close to the mean. A large deviation means it's spread out, it's not very accurate, the data's all over the place. So what was the issue? And you might have seen this graph in the news. The graph was this right here. Has the same bar in both graphs at the same height. And what this was hospital capacity. And the idea was if we all kept going out, we would have, everyone would be sick around the same point in time. There'd be about a month of just pure hell where everyone gets sick, but that would be an extreme high spike, an extreme high number of people that were sick at the same time. And the problem is our hospitals only have capacity for so many people. And so the second that we have more people sick than we have the capacity to hospitalize, that's when people start dying. And the whole point of isolation, the whole entire point of putting people into isolation was to forcefully get a large deviation, to get a large distribution. So instead of concentrating everything towards the month that it happened or the couple of months that it happened, we wanted to spread it out over more time. Does that mean less people get sick? No, the exact same number of people are going to get sick in the long run. There's no difference in the number of people that get sick. It's the difference of how many people get sick at one point in time. And if we could spread out the time in which people get sick, then we would always stay below that hospital capacity. So that was the whole point of being isolated and staying at home, was not to change how many people get sick, it was to change how many people get sick in a given time frame. We need it to spread out over time. We need a large deviation, a large distribution, so we're never ever above our hospital capacity. So I hope that explanation makes sense for you. Good luck in this section.